lab, coming into a physics lab and seeing a frictionless track and oscilloscopes and all kinds of things, I mean, would that conjure images of the real world? I thought, I'm not going to use these labs that, have these sterile equipment and experiment and don't really connect physics to the real world. And then I thought, physics is all around us. I wouldn't go chase that down, but, physics is everywhere. Let's use the real world as our laboratory. Let's not use the equipment in the lab, but let's just use consumer devices. These phones take pictures at 240 frames per second. You could just film the motion of a ball thrown up or a person walking or a punching and then analyze it at 240 frames per second, upload it, track the video, and make graphs. Let's use these instead of, sensors that students don't know how they work and it's all hocus pocus and magic. So I decided to transform the lab to the real world. The last one gave me some pause. In order to be successful, the case must have a component of empathy or social good. Yes, the business school. So, for example, each case starts with the word you. You have been appointed to help a family invest in inheritance. And so you're put in a position to help somebody, an entity, a person, or society. How do you do that with physics? I had no idea at first, but it shows that, we're so constrained in our thinking about teaching because we never give ourselves an opportunity to think out of the box. I'll show you how we did that. So here are the 6 projects, and the names won't mean very much to you. We started as a drag race to warm them up to kinematics, and they have to build a Rube Goldberg machine that has 7 different steps. One has to have an elastic collision, another inelastic collision, another one has to have a trajectory, one has to involve a pulley and rotational motion, and so on. There are restrictions. One has to have a, what a Rube Goldberg machine is. One is one of these machines that does a lot but accomplishes very little. In this case, it has to crack open an egg at the last step. And then the students have to measure all of the momentum and energy transfers in the entire machine throughout all of the steps. Now, measuring momentum on a Pascal card with a frictionless card is relatively easy, but also rather non-interesting. Here, you have to use the skills developed with measuring motion with your own cell phone and digitizing the graphs in order to do that. So the physics is actually quite rich. And then the third one, which I'm going to discuss, is the spin focusing. It deals with the part of the curriculum that has vibrations, oscillations, waves, and sound. So at the beginning of the project period, the students receive a brief that gives them all of the information. How do I hook the students? How many of you know about El Sistema? El Sistema. 2 years ago, Jose Abreu, an economist from Caracas, Venezuela, got an honorary doctorate for studying El Sistema. Where I presented the directive underpinnings of today's talk. So today that will be very different theory. I'm more focused on the exploration program. Fusion. If you want to diffuse enough atmospheric pressure, you need a confinement time of the order of seconds. The confinement time is the energy of the plasma divided by the heating power that you need to sustain this energy. So it's the characteristic time scale on which the plasma would cool down if you turn off the heating. This is the order of 100 seconds. And to achieve fusion, you need a temperature of 10 kV or so, which means the thermal velocity of ions exceeds 1,000 kilometers per second. So if you don't confine it, the lifetime confinement time would be less than 1 second. Therefore, you use magnetic fields, as I'm sure you all know. In the magnetic field, charges can essentially only move along the field. Across the field, they move in tightly wound spirals with a gyro radius of the order of equal to the perpendicular velocity component divided by the gyro frequency, which is charge times speed to the mass. So magnetic field provides the particles in 2 of the 3 dimensions, and the obvious way to provide confinement in the 3rd dimension is to bend the magnetic field into a ring. But that doesn't quite work. If you do that, and you make the radius of the field capital R be much larger than 1, and the gyro radius obviously, so you have a small parameter, goes out. So if you practice it, it's order 10 to the minus 3, then the magnetic field is necessarily non-uniform. So the particles do not anymore exactly follow the Z lines after gyration. In addition, the velocity vector, the time average velocity vector, consists not only of the time velocity along the field, so the unit vector along the field, there's also a slower by a factor rho star drift, perpendicular to the Z lines and perpendicular to the field strength. So there's a slow drift
which is three orders of magnitude slower than the parallel motion. So if you just bend the field into a ring, the particles will slowly increase in the vertical current. Because gravity is obviously equals. In doing so, there's a constant quantity that will indicate a ultimately for getting moment of the different current loop that is faster length. So the confinement time of such a device would then be, roughly speaking, the length of the device divided by the drift velocity, which is one factor of rho star smaller than the total velocity. So you've gained 3 orders of magnitude in confinement time, which you need another 3 orders of magnitude. So the way to get so what we need is second order confinement, second order in rho star. The most popular way of achieving that is to bend the magnetic field so that it spirals around a toroidal surface, such as it's called a Fokker map. The idea was used at Talmud Zahar in 1951, but others conceived of the idea simultaneously. So in a Fokker map, you drive a current of order of megaamperes, which then produces a toroidal field that adds to the toroidal field and makes the field lines spiral around the plasma. What then happens can be illustrated by movie here. So this is a movie of a particle orbit. So as you see the particle orbit, the particles follow the magnetic surface placed up by the field lines, but the field surface is color-coded. Color-coded. The drift is vertical, but the particle drifts into the plasma as much as it drifts out of it. So in this way you get second order confinement. But you have to drive this current. And there's no obvious way of driving the current in steady state in the plasma. And that current can be the source of instabilities, of the violent instabilities. The Fokker map was not